The morning of September 7th, 1944, near the French village of Issy-sur-Mer, American ordnance officers stood in a muddy field staring at something they had been told was nearly indestructible. Before them sat a German Panzerkampfwagen Tiger Ausführung B, known to Allied intelligence as the King Tiger or Tiger II. It was enormous. The turret alone rose nearly 8 feet above the ground. The glacis plate, sloped at 50 degrees, was 6 inches thick at its face. The whole machine weighed nearly 70 tons fully loaded. This particular Tiger II had been abandoned by its crew 2 days earlier. Not destroyed by enemy fire, not disabled by aerial bombardment, simply abandoned on the side of a road leading out of Normandy, its engine silent, its tracks still. French resistance fighters had found it first and reported its location to American forces, advancing through the Bocage country. Engineers from the 1st Army's Ordnance Section arrived with recovery vehicles and spent hours examining the tank before attempting to move it. What they found confused them. There was no visible combat damage. The armor showed no penetrations. The tracks were intact. The suspension appeared functional. The gun, that massive 88mm KUK 43L/71, was undamaged and still had ammunition in its ready racks. Yet the crew had walked away, leaving behind what German propaganda had proclaimed as the most powerful tank in the world. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. An American captain climbed onto the rear deck and opened the engine compartment hatches. Inside, the Maybach HL230P30 engine looked intact. No obvious battle damage. No signs of catastrophic mechanical failure that would explain abandonment. He ordered his men to investigate the transmission. What they discovered there would begin to answer a question that had puzzled Allied armor commanders since the first King Tigers appeared in combat 3 months earlier. Why were so many of these supposedly invincible machines found abandoned on roadsides across France? Why did German crews, who had been trained to fight to the last round, simply walk away from functional weapons systems? The answer was not what anyone expected. It was not about Allied air superiority or superior American tactics or even the numerical advantage the Allies enjoyed in Normandy. The answer was mechanical. It was mundane. It was about transmissions and final drives and the reality of German industrial production in 1944. This Tiger II would be transported to a testing facility. American engineers would start its engine and drive it under controlled conditions. They would measure its performance, document its failures, and compile reports that would fundamentally change how Allied intelligence assessed German armoured capabilities. What they would discover was this: the most powerful tank Germany ever produced, the culmination of years of design, evolution, and technological refinement, could barely function as a combat vehicle. Not because of any flaw in its conceptual design, not because German engineers lacked skill or knowledge, but because by September 1944, Germany could no longer build what its engineers designed. The gap between blueprint and reality had become a chasm, and that gap was killing German tank crews just as surely as Allied guns. To understand what American engineers found when they tested captured King Tigers, one must first understand what the Tiger II represented in German military thinking. The tank was not simply a weapon. It was an ideology made steel. It embodied a particular philosophy of armoured warfare that had developed in Germany over the previous decade, a philosophy that prioritized individual vehicle superiority over numerical advantage. The roots of this thinking stretched back to 1940, to the early campaigns in France and the Low Countries. German panzer divisions had achieved stunning victories not through superior numbers, but through superior tactics, coordination, and the shock value of concentrated armour. Commanders like Heinz Guderian had proven that properly employed armoured forces could achieve breakthrough and exploitation far beyond what pre-war military theorists had considered possible. These victories created a narrative within the German military establishment. Quality could overcome quantity. Superior engineering could compensate for industrial limitations. A smaller number of excellent tanks could defeat a larger number of mediocre ones. This narrative intensified after 1941, when German forces invaded the Soviet Union and encountered the 34 for the first time. Soviet tank designers had created something unexpected, a medium tank with sloped armor, a powerful 76mm gun, wide tracks for mobility in mud and snow, and a diesel engine. German tanks of 1941, the Panzer III's and early Panzer IV's, were suddenly outmatched. The response was predictable. Germany would build bigger tanks, heavier armor, more powerful guns. Better engineering would solve the problem. The Tiger I appeared in 1942, mounting an 88mm gun and frontal armor up to 4 inches thick. It was formidable in combat when it worked. Reports from the Eastern Front described Tiger companies stopping entire Soviet tank battalions. A single Tiger could engage and destroy multiple 34s before they could close to effective range. German propaganda seized on these successes, creating an aura of invincibility around the Tiger. But the Tiger I had problems. It was mechanically complex, requiring extensive maintenance. Its weight, 45 tons, strained its transmission and final drives. It consumed fuel at a prodigious rate, limiting its operational range. Production was slow, expensive, and required skilled labor that Germany increasingly lacked. By 1943, as the war turned decisively against Germany, these limitations became critical. Yet, instead of simplifying designs or focusing on production efficiency, German designers doubled down on the quality over quantity philosophy. The Tiger II was conceived in early 1943 as the Tiger I's successor. It would be heavier, better armored, and mount an even more powerful gun. The specifications were ambitious. Frontal hull armor would be 150mm thick, sloped at 50 degrees to provide effective protection equivalent to over 200mm against anti-tank fire. Turret front armor would be 180mm thick. The main gun would be the 88mm KK-43, a long-barreled weapon with a muzzle velocity of 3,300 feet per second, capable of penetrating any Allied tank at ranges exceeding 2,000 meters. The design team, led by engineers at Henschel and Sohn, created something that on paper was nearly perfect. Ballistic tests proved the armor was essentially immune to frontal penetration by any Allied tank gun in service. The 88mm gun could destroy any Allied armor from distances where return fire was impossible. German crews, who trained on the Tiger II, reported feeling invincible inside its thick armor. This was the weapon that would restore German armored superiority. This was the tank that would stop the Allied advance. Production began in January 1944 at factories in Kassel. Each Tiger II required approximately 300,000 man-hours to build, involving thousands of individual parts and extensive precision machining. In a fully functioning industrial economy with abundant resources and skilled labor, this might have been manageable. But Germany in 1944 was not operating under those conditions. By the time the first Tiger IIs rolled off assembly lines in early 1944, Germany's industrial capacity was collapsing under pressures that no amount of engineering excellence could overcome. Allied strategic bombing had begun systematically targeting German industrial facilities. American 8th Air Force and Royal Air Force Bomber Command flew thousands of sorties against factories, rail yards, oil refineries, and production centers. The attacks were not uniformly successful, and German industry proved remarkably resilient, but the cumulative effect was devastating. Steel production, the foundation of all heavy manufacturing, declined steadily throughout 1944. Germany had begun the war with access to high-grade iron ore from Sweden and captured territories in France. By mid-1944, Allied advances had cut off French sources, and British naval operations made Swedish imports increasingly unreliable. Domestic German iron ore was lower grade, requiring more processing to achieve the same steel quality. Alloying elements, particularly nickel, chromium, and molybdenum, which were essential for producing the hardened armor plate German tanks required, became critically scarce. The steel that went into Tiger Eyes built in September 1944 was not the same steel that had been used in Tiger Eyes built in 1942. Metallurgical analysis conducted on captured German armor after the war revealed significant variations in composition and quality. Armor plates from late-war German tanks showed higher sulfur content, lower alloy percentages, and inconsistent heat treatment. This affected the armor's ballistic properties, making it more brittle and prone to cracking when struck by armor-piercing rounds. Some plates shattered on impact rather than deflecting projectiles as properly hardened armor should. But steel quality was only one problem among many. Precision manufacturing, essential for complex mechanical systems like tank transmissions, requires machine tools, skilled workers, and time. Germany was losing all three. Machine tool production declined as factories were bombed and resources diverted. Skilled workers were conscripted into the Wehrmacht to replace casualties on the eastern and western fronts. The men and women who remained in factories were increasingly forced laborers from occupied territories, prisoners of war, or concentration camp inmates who had no incentive to produce quality work and every reason to sabotage production when possible. Quality control, which in peacetime would have caught defective parts before they were installed, broke down. Inspectors were overworked. Testing was abbreviated. Parts that would have been rejected in 1940 were accepted in 1944 because the production quotas had to be met. Ministry of Armaments officials, under pressure from Hitler to deliver more tanks more quickly, approved compromises that would have been unthinkable earlier in the war. Specifications were relaxed. Testing protocols were shortened. Components that failed preliminary tests were sometimes installed anyway. The transmission installed in the Tiger II was a particular victim of these declining standards. The Maybach Ulvar B401216B transmission was a complex piece of engineering, a semi-automatic unit with 8 forward gears and 4 reverse gears. It had been designed to handle the torque of the Maybach engine and the weight of a 45-ton Tiger I. The Tiger II weighed 70 tons. Engineers knew this was a problem. Test reports from early 1944 noted that the transmission was undersized for the vehicle's weight. Recommendations were made to develop a stronger unit, but development takes time, and time was something Germany did not have. The Tiger II entered production with a transmission designed for a lighter vehicle, manufactured with declining material quality, assembled by inexperienced workers, and installed with abbreviated testing. German tank crews received no information about these compromises. They were told they were getting the best tank in the world, and they believed it because they wanted to believe it, because the alternative was unthinkable. The Tiger II, captured near Isigny, was transported by rail to the port of Cherbourg in late September 1944. From there, it was loaded aboard a Liberty ship bound for the United States. It arrived at the port of Baltimore in mid-October and was transported by heavy truck to the Aberdeen Proving Ground in Maryland, the United States Army's primary facility for testing ordnance and armor. Aberdeen had been testing captured German equipment since 1942. Engineers there had examined Panzer III, Panzer IVs, and even a Tiger I that had been captured in Tunisia. They had developed systematic protocols for evaluating foreign times. Armor. Measure the armor thickness at multiple points. Test the metallurgy. Examine the internal layout. Start the engine and drive the vehicle under controlled conditions. Document any mechanical failures, and compile comprehensive reports for distribution to Army Ground Forces and the Armoured Board. The Tiger II that arrived at Aberdeen in October was assigned to a team led by Captain James Bellinger, an engineering officer who had worked in the automotive industry before the war. Bellinger's team included mechanical engineers, metallurgists, and experienced tank mechanics who had worked on everything from light tanks to the heaviest American armor. They approached the Tiger II with professional curiosity tempered by caution. This was the tank that intelligence reports claimed could destroy any Allied armor from 2,000 meters. This was the vehicle German propaganda called unstoppable. Initial examination took 3 weeks. Every dimension was measured and recorded. Length, overall, 33 feet 9 inches, including the gun. Width, 12 feet 3 inches. Height, 10 feet 1 inch. Combat weight, 69.8 tons. The measurements confirmed what visual inspections suggested. This was the largest, heaviest tank yet deployed by any nation in the war. The armor thickness exceeded anything previously encountered. The glacis plate measured 150 millimeters at 50 degrees. The turret front was 180 millimeters. Even the side armor was 80 millimeters thick. Metallurgical samples were taken from the armor plate using drilling equipment. The samples were analyzed in Aberdeen's laboratory facilities. The results were interesting. The armor was face-hardened steel, made brittle on the outer surface to shatter incoming projectiles while maintaining a tougher interior core. The hardness values were acceptable, though not exceptional. The chemical composition showed lower alloy content than expected for armor of this quality specification. There were inclusions in the steel, microscopic impurities that indicated less than ideal manufacturing conditions. The armor was good, but not perfect. It would likely perform adequately in combat, though perhaps not to the standard German engineers had intended. The internal layout was examined next. The fighting compartment provided approximately 200 cubic feet of working space for the crew of 5: commander, gunner, loader, driver, and radio operator, who also served as hull machine gunner. This was far more spacious than Japanese tanks, comparable to American heavy tanks. Each crew member had a defined position with adequate room to perform their tasks. The commander had a cupola with periscopes providing all-around vision. The gunner had an articulated telescopic sight, the TZF-9D, with magnification for long-range engagement. The loader had access to well-organized ammunition racks holding rounds for the main gun. The driver's position was particularly well designed. He had excellent vision through a periscope system and direct vision port. His controls included a steering wheel, rather than the levers used in most tracked vehicles, connected to a hydraulically assisted system that made maneuvering easier. The radio operator to his right had a ball-mounted machine gun, the MG-34, with adequate traverse and elevation. Everything about the internal arrangement suggested thoughtful design by engineers who understood crew efficiency and combat effectiveness. The main gun drew extensive attention. The 88mm K80A-43L/71 was a formidable weapon. Its barrel length was 71 calibers, meaning the bore was 71 times the diameter, approximately 6.2 meters long. Test firing at Aberdeen's range demonstrated its capabilities. With standard armor-piercing ammunition, the gun could penetrate 7 inches of armor plate at 1,000 meters. At 2,000 meters, penetration was still over 5 inches. No Allied tank in service had frontal armor exceeding 4 inches. The implications were clear. The Tiger II could destroy any Allied armor at ranges where return fire was impossible. On November 9, 1944, Captain Bellinger's team completed their static examination and prepared for mobility testing. The goal was simple: start the engine, drive the tank through Aberdeen's test courses, and document its performance and any mechanical issues. The Maybach HL230P30 engine started without difficulty. It was a V12 gasoline engine producing 700 horsepower at 3,000 revolutions per minute. The distinctive sound of the engine at idle was deeper than American tanks, a low rumble from the 12 cylinders. The first test drive began at 0900 hours on November 10th. The driver selected first gear using the steering wheel-mounted controls. The semi-automatic transmission engaged. Smoothly, the Tiger II began moving forward across Aberdeen's flat test range. The acceleration was sluggish, predictable for a vehicle weighing nearly 70 tons. Maximum speed on the paved test track reached 25 miles per hour, lower than the specification of 28 miles per hour, but acceptable given the vehicle's weight and the caution exercised during initial testing. Observers noted that the ride quality was surprisingly good. The torsion bar suspension absorbed bumps effectively. The interleaved road wheel arrangement, with overlapping wheels on alternating sides of the hull, distributed weight efficiently and provided a stable platform. From a purely performance standpoint, the Tiger II moved with a grace that seemed impossible for something so massive. Bellinger, watching from a jeep following behind, was impressed despite himself. The first indication of trouble came after approximately 15 kilometers of driving. The test driver reported difficulty shifting gears. The semi-automatic transmission, which should have shifted smoothly between ranges, was becoming resistant. The driver had to use increasing force on the steering wheel controls to engage the next gear. Engineers monitoring the test noted this in their logs but continued the evaluation. Mechanical systems often required break-in periods. New tolerances needed to settle. This might be normal. After 25 kilometers, the gear shifting problem worsened. The transmission began grinding between shifts, a sound that made the experienced mechanics in Bellinger's team grimace. Grinding meant metal contacting metal without proper lubrication or synchronization. It meant parts wearing rapidly, shearing off microscopic fragments that would circulate through the transmission fluid and cause accelerating damage. The test was halted. The Tiger II was returned to the maintenance shed for inspection. Mechanics drained the transmission fluid and examined it. The fluid was dark, contaminated with metal particles visible to the naked eye. This was abnormal for a transmission with less than 30 kilometers of operation. The amount of metal debris suggested extensive internal wear. The transmission was partially disassembled. Engineers found that the synchronizer rings, which allowed smooth gear engagement, were already showing wear patterns consistent with hundreds of hours of operation, not a single day of testing. The metallurgy of the synchronizer components was tested. The results explained the rapid wear. The parts were made from steel with insufficient hardness. They should have been case-hardened to provide a wear-resistant surface, but the hardening appeared inadequate or improperly executed. Under the stress of shifting a 70-ton vehicle, the soft metal was abrading rapidly. At the current wear rate, the transmission would fail completely within 100 to 150 kilometers of operation. Bellinger included this finding in his preliminary report dated November 17, 1944. The report noted that the Tiger II's transmission was inadequate for the vehicle's weight and combat conditions and predicted rapid mechanical failure under operational use. The report was distributed to Army Ground Forces Headquarters, to the Armoured Board at Fort Knox, and to intelligence sections responsible for assessing German armour capabilities. But the testing continued. Aberdeen's mission was not merely to identify problems, but to document exactly how and when systems failed. The Tiger II was fitted with a rebuilt transmission using parts cannibalized from German supply stocks captured in France. On November 23rd, testing resumed. This time, engineers monitored temperatures at multiple points on the transmission housing using contact thermometers. They wanted to understand if heat buildup was contributing to the failures. The second test drive began well. The rebuilt transmission shifted smoothly through the first 10 kilometers. Then the temperature readings began climbing. The transmission housing reached 80 degrees Celsius after 15 kilometers, 90 degrees after 25 kilometers. At 30 kilometers, the temperature exceeded 100 degrees Celsius. This was far above normal operating temperature for a vehicle transmission. At these temperatures, lubricating oil breaks down, losing its protective properties. Metal parts expand, changing tolerances that engineers had calculated for normal temperatures. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. At 38 kilometers, the driver reported the transmission was locked in third gear. He could not shift up or down. The Tiger II limped back to the maintenance facility operating in a single gear, its engine laboring. Inspection revealed that internal components had expanded from heat, binding, against their housings. The synchronizer rings, already weakened from improper hardening, had partially seized. The transmission was destroyed, its components damaged beyond field repair. Aberdeen was not the only facility testing captured Tiger IIs. In England, a king tiger captured near Vimoutiers in France during the Falaise Pocket Battle was undergoing evaluation at the School of Tank Technology in Chertsey. British engineers were discovering the same problems American teams found at Aberdeen. Their Tiger II, which had been driven approximately 50 kilometres by its German crew before abandonment, showed identical transmission wear patterns. The British report, compiled in December 1944, noted that the Tiger II's final drives, the reduction gears connecting the transmission to the drive sprockets, were also failing prematurely. These components were designed to handle the torque of the engine while reducing rotational speed for the tracks. In the Tiger II, they were undersized for the vehicle's weight. British testing revealed stress fractures in the final drive housings after minimal operation. The fractures would eventually lead to complete failure, leaving the tank immobile. Intelligence officers began correlating these technical findings with field reports from France and Belgium. Throughout the autumn of 1944, Allied forces advancing through Western Europe had encountered numerous abandoned Tiger IIs. Initially, these abandonments were attributed to fuel shortages or crew decisions to retreat before being encircled. But when recovery teams examined the abandoned vehicles, a pattern emerged. Many showed no combat damage, but had catastrophic mechanical failures. A Tiger II found near the Belgian village of Stavelot in December 1944 had a seized transmission with internal components welded together by heat and friction. Another discovered outside Bastogne during the Battle of the Bulge had both final drives fractured, the drive sprockets hanging loosely from their mounts. A third, abandoned on the road to Houffalize, had thrown a track because the interleaved road wheel system had frozen solid, packed with mud and ice that prevented the wheels from rotating independently. The interleaved road wheel design, which provided such excellent weight distribution and ride quality, was itself a source of mechanical problems. The overlapping wheels meant that mud, snow, and debris could pack between them. In winter conditions, this material froze solid overnight. German crews discovered that starting a Tiger II on cold mornings was nearly impossible if the wheels had frozen. The engine lacked sufficient power to break the frozen wheels loose. Crews had to light fires under the suspension to melt the ice, a process that took hours and revealed their position to Allied artillery observers. Even when the running gear functioned, the tracks themselves were problematic. Each track link on the Tiger II weighed approximately 10 kilograms. The complete track assembly weighed over 3 tons per side. The tracks were 918 millimeters wide to distribute the vehicle's weight and reduce ground pressure. But this width meant the Tiger II could not cross standard bridges or travel on most European roads without destroying pavement. German tank transporters, the heavy trucks designed to move tanks by road, could not accommodate the Tiger II's width with its combat tracks installed. This created an operational nightmare. To move Tiger IIs by rail or road, crews had to remove the combat tracks and install narrower transport tracks. This process required jacks, tools, and several hours of work. At the destination, the process had to be reversed before the tank could enter combat. Units arriving at the front often found themselves spending entire days just preparing their vehicles for action. The complexity meant that Tiger II units had far fewer tanks operationally ready at any given time compared to units equipped with simpler vehicles. American intelligence compiled these findings into a comprehensive assessment distributed in January 1945. The report concluded that the Tiger II, while formidable when functioning properly, was mechanically unreliable and unsuited for sustained combat operations. It noted that the average operational range before major mechanical failure was approximately 150 kilometers, barely sufficient for a single day of mobile warfare. By comparison, an American M4 Sherman could operate 500 kilometers between major maintenance. Soviet 34s routinely exceeded 1,000 kilometers. The implications were profound. Germany had invested enormous resources into building what its engineers designed as the ultimate tank. Each Tiger II cost approximately 800,000 Reichsmarks to produce, equivalent to the cost of building 8 Panzer IV medium tanks or 21 Stug, 30i assault guns. The production time per unit was approximately 3 times longer than standard German armour. Germany built only 489 Tiger IIs during the entire production run from January 1944 to March 1945. Those 489 vehicles absorbed factory capacity, skilled labour, and resources that could have produced thousands of simpler tanks, and they failed mechanically at rates that made them questionable investments. German tank commanders in the field began requesting they be re-equipped with older, less impressive but more reliable vehicles. Crews who had initially been proud to serve in King Tiger units became frustrated with machines that spent more time under repair than in combat. The technical reports compiled at Aberdeen and Chertsey told only part of the story. Behind the statistics about transmission failures and final drive fractures were German tank crews who discovered the gap between propaganda and reality in the worst possible way, under combat conditions when their lives depended on their equipment functioning as promised. Oberleutnant Hans von Luck, commanding a company of Tiger IIs in Schwer Panzerabteilung 503 during the Ardennes offensive in December 1944, kept a diary that was recovered after the war. His entries from mid-December provide insight into the psychological impact of mechanical unreliability on combat effectiveness. On December 14th, he wrote that 2 of his company's 8 Tiger IIs had broken down during the approach march to jumping-off positions. The transmissions had failed. The tanks were abandoned because recovery vehicles could not reach them before American forces overran the area. On December 17th, another Tiger II threw a track when the interleaved road wheels seized from frozen mud. The crew spent 4 hours attempting repairs under artillery fire before abandoning the vehicle. Von Luck noted bitterly that his company had lost 3 tanks without firing a shot at the enemy. By December 23rd, only 3 of his original 8 Tiger IIs remained operational. The others had been abandoned due to mechanical failures, not combat damage. His final entry from the Ardennes, dated January 4, 1945, recorded that his last functioning Tiger II had suffered a final drive failure and could not be recovered. His company was withdrawn from combat and never re-equipped. Similar accounts emerged from other units. Schwer Panzerabteilung 507, fighting in Hungary in early 1945, reported that of 14 Tiger IIs assigned to the battalion, an average of only 4 were combat-ready on any given day. The others were undergoing repairs, awaiting spare parts, or had been abandoned due to irreparable damage. Battalion records show that more Tiger IIs were lost to mechanical breakdown than to enemy action throughout the unit's combat history. German tank crews, trained to serve in Tiger IIs, received extensive instruction on the vehicle's capabilities, but minimal information about its limitations. Training emphasized the superiority of German armor and engineering. Instructors told new crews they would be operating the most powerful tank in the world, capable of destroying any enemy armor while remaining invulnerable to return fire. This created expectations that combat experience quickly shattered. A captured Tiger II crewman, interviewed by American intelligence officers in February 1945, described his unit's experience. They had received their tanks in November 1944 and spent 3 weeks training at Paderborn before deployment to the Western Front. During training, 1 tank suffered a transmission failure. They were told it was an isolated incident, a manufacturing defect in that particular vehicle. In combat, within 2 weeks, 3 of their company's 9 tanks had mechanical breakdowns requiring major repairs. Crews began losing confidence not in their fighting ability, but in their equipment's reliability. The psychological impact was corrosive. Tank crews depend on trust in their equipment. When a tank's armor fails to protect them or its gun fails to fire, crews lose the confidence necessary to fight effectively. But mechanical unreliability created a different kind of psychological stress. Crews never knew if their tank would function when needed. Every mission began with uncertainty. Would the transmission hold? Would the final drives survive the approach march? Would they reach the battlefield or be left stranded on some muddy road, vulnerable to air attack or enemy advance? This uncertainty affected tactical decision-making. Tank commanders became cautious about maneuvering, knowing aggressive movement increased mechanical stress. They avoided difficult terrain that might break already stressed components. They conserved engine hours, reducing training and maintenance checks that might have prevented failures. The tactical doctrine emphasizing mobility and aggressive action that had made German panzer forces so effective early in the war became impossible to execute when the tanks themselves could not be relied upon to move. German maintenance crews worked desperately to keep Tiger IIs operational, but they faced impossible challenges. Spare parts were scarce. Manufacturing priorities focused on producing new vehicles, not replacement components for existing ones. When transmissions failed, there were often no replacements available. Final drives that fractured could not be repaired in field conditions. The complex interleaved roadwheel system required specialized tools and hours of labor to service properly, time that frontline units rarely had. By early 1945, some German commanders were requesting they not be sent Tiger IIs as replacements. They preferred older Panzer IVs or Stug assault guns. These vehicles were less impressive on paper, less capable in direct comparison, but they were reliable. They could be maintained with available resources. They functioned when needed. A working Panzer IV was worth more than a broken Tiger II, and in the desperate defensive battles of early 1945, reliability mattered more than theoretical superiority. The Tiger II's mechanical failures represented more than poor engineering or manufacturing defects. They represented the collision between German military ambition and industrial reality in the final years of the war. Understanding why the Tiger II failed requires understanding the state of German industry in 1944 and 45 and the impossible demands placed upon it. Germany's war economy in 1944 was simultaneously producing more weapons than ever before while collapsing under accumulated strain. Armaments Minister Albert Speer had achieved remarkable increases in production through organizational reforms, rationalization of manufacturing, and ruthless exploitation of forced labor. Tank production reached its peak in December 1944, with over 1,500 armored vehicles of all types completed that month. But this production came at tremendous cost. The quality of materials declined steadily throughout 1944. Steel production remained relatively high in absolute numbers, but the composition of that steel changed as access to alloying elements decreased. Nickel, essential for armor plate, came primarily from mines in Finland and New Caledonia. Finland signed an armistice with the Soviet Union in September 1944, cutting off German access to Finnish nickel. New Caledonia had been in Allied hands since early in the war. Chrome, another critical alloying element, came from Turkey. Turkish chrome shipments to Germany declined sharply in 1944 as Turkey moved toward neutrality and eventually joined the Allies in February 1945. Without adequate alloying elements, German steel manufacturers compensated by adjusting heat treatment processes and adding substitute materials. The resulting armor plate was harder but more brittle. When struck by armor-piercing rounds, late-war German armor often cracked or shattered rather than deflecting projectiles. Metallurgical analysis of Tiger II armor from vehicles built in late 1944 shows significantly different properties than armor from earlier production. The later armor met minimum hardness specifications but lacked the toughness that would have made it truly effective protection. Precision manufacturing suffered even more dramatically than material quality. The transmission and final drive failures that plagued the Tiger II resulted partly from inadequate design, but more fundamentally from manufacturing quality control failures. These components required machining tolerances measured in hundredths of millimeters. Gears had to be cut precisely to mesh, smoothly under load. Bearings required carefully ground surfaces to reduce friction. Heat treatment had to be controlled exactly to achieve proper hardness without causing brittleness. German machine tool production in 1944 was approximately 40% of 1942 levels. The machine tools that remained in service were worn from continuous operation without adequate maintenance. Skilled machinists were increasingly scarce as conscription pulled workers into the military. The workforce that remained included forced labourers from occupied territories who had neither training in precision manufacturing nor incentive to produce quality work. Sabotage was common. Parts that appeared acceptable might have been deliberately made slightly out of specification, enough to pass cursory inspection, but insufficient to function properly under stress. Quality control inspectors, who in peacetime would have rejected components failing to meet specifications, faced pressure to approve marginal parts to meet production quotas. Ministry of Armaments. Officials established production targets that took priority over quality standards. A transmission that might fail after 150 kilometers of operation was approved because the alternative was missing monthly production quotas. The assumption was that 150 kilometers was sufficient for current combat conditions, that Germany was fighting a defensive war where long-range mobility mattered less than immediate availability. This assumption ignored tactical reality. Even in defensive operations, tanks required mobility to move between threatened sectors, to launch counterattacks, to withdraw when positions became untenable. A tank that could only operate 150 kilometers before major mechanical failure was effectively a static fortification with severe limitations. And unlike true fortifications, it consumed fuel, spare parts, and maintenance resources, while providing only temporary defensive capability. The Tiger II's fuel consumption created additional operational problems. The Maybach engine consumed approximately 500 litres of fuel per 100 kilometres of operation. The vehicle's fuel tanks held 860 litres, giving a theoretical range of 170 kilometres on roads. But combat operations consumed fuel more rapidly than road marches. Manoeuvring, idling in position, running the turret traverse motors, operating radios and other electrical systems all drew power from the engine. In practice, operational range was closer to 120 kilometers before refueling. Germany's fuel supplies in late 1944 were critically limited. Synthetic fuel plants, which produced the majority of German gasoline and diesel, were priority targets for Allied strategic bombing. Production declined from approximately 200,000 tons per month in early 1944 to less than 30,000 tons per month by December. Natural oil supplies from Romania, which had provided approximately 60% of Germany's crude oil, were cut off when Soviet forces occupied the Ploiești oil fields in August 1944. Tank units competing for scarce fuel found that Tiger II companies consumed disproportionate amounts relative to their combat effectiveness. A company of 14 Tiger IIs might consume as much fuel as a full battalion of Panzer IVs while providing far fewer operationally ready vehicles. Some commanders began viewing Tiger II assignments as burdens rather than assets, prestigious units that consumed resources without delivering commensurate combat power. The story of the Tiger II's mechanical failures at Aberdeen Proving Ground and in combat service across Europe contains lessons that extended far beyond the immediate tactical situation of 1944 and 45. It demonstrated fundamental principles about industrial warfare, about the relationship between design, ambition, and manufacturing reality, and about the limitations of pursuing technological superiority without adequate industrial capacity to support it. American military analysts studying the Aberdeen test reports in early 1945 drew explicit conclusions about armor development philosophy. The United States had pursued a different path than Germany. American tank designers prioritized reliability, ease of maintenance, and mass production over individual vehicle superiority. The M4 Sherman was not the best tank in the world by any individual metric. German tanks had thicker armor, Soviet tanks had better guns, but the Sherman could be built in enormous quantities, maintained with available resources, and operated reliably under diverse conditions. The Sherman's design incorporated lessons from American industrial practice. Components were standardized wherever possible. The transmission, while not sophisticated, was robust and could be maintained by mechanics with standard tools. The engine, whether the radial aircraft engine in early models or the General Motors diesel in later versions, used proven designs from existing production lines. The suspension was simple, easily repaired, and required minimal specialized equipment. When a Sherman broke down, which happened far less frequently than German tanks, it could usually be repaired quickly and returned to service. This design philosophy reflected American industrial advantages but also represented conscious choices about how to employ those advantages. American engineers could have designed more complex, more powerful tanks. Experimental vehicles like the 29 heavy tank, developed late in the war, mounted a 105mm gun and had armor up to 7 inches thick. But these vehicles remained experimental because military planners recognized that complexity and individual superiority mattered less than availability and reliability. The Tiger, II, represented the opposite philosophy taken to its logical conclusion. German designers, working under severe resource constraints, chose to concentrate available capacity on fewer, theoretically superior vehicles. Each Tiger II was supposed to be worth multiple enemy tanks, but this calculation failed when mechanical unreliability meant those superior vehicles spent most of their time under repair rather than in combat. A tank that could destroy any enemy but only operated 150 kilometers before breaking down provided less combat value than a simpler tank that operated reliably for thousands of kilometers. Soviet tank designers reached similar conclusions through different experiences. The 34 medium tank was deliberately designed for simplicity and ease of production. Its armor was welded rather than interlocked, a faster manufacturing process requiring less skilled labor. Its transmission was crude but functional. Its engine was a diesel, less refined than German gasoline engines, but more fuel-efficient and less prone to fires. Soviet factories could build 34s in quantities that overwhelmed German defenses through sheer numbers. Quality control was often poor. Individual tanks might be mechanically unsound, but enough worked well enough to achieve operational objectives. The British, operating with industrial capacity between American and German levels, initially pursued quality-oriented designs similar to German philosophy. The Cromwell and Comet cruiser tanks were well-engineered, sophisticated vehicles with good performance characteristics. But British tank units in northwest Europe achieved their greatest successes when equipped with American Shermans, which proved more reliable under campaign conditions than British designs. Post-war British armour development increasingly emphasised reliability and maintainability over individual performance metrics. The Tiger II's legacy in post-war armour development was thus primarily cautionary. It became a case study in what not to do, an example of pursuing technological sophistication beyond industrial capacity to support. Modern tank development, whether American, Soviet, British, or other nations, consistently prioritized reliability alongside performance. The recognition that a tank must function reliably under field conditions became as fundamental as firepower and protection in design philosophy. For the German tank crews who served in Tiger IIs, the experience left lasting impressions. Veterans interviewed decades after the war consistently mentioned mechanical unreliability as their primary frustration. They had believed they were operating superior equipment. They discovered instead that they were trapped in complex, fragile machines that failed when needed most. Some expressed anger at leadership that sent them into combat with inadequate equipment, while propaganda proclaimed German technological superiority. Others simply noted the bitter irony that Germany's most powerful tank was ultimately defeated not by enemy weapons, but by its own mechanical limitations. The Tiger II, captured near Sydney, tested at Aberdeen Proving Ground, and documented in technical reports, remains in storage at the United States Army Ordnance Museum collection. It stands as physical evidence of the gap between design, ambition, and manufacturing reality that characterized German industrial production in the final years of World War II. The transmission that failed after 150 kilometers of testing, the final drives that fractured under operational loads, the interleaved road wheels that froze solid in winter conditions, all remain as components of a vehicle that represented both the height of German engineering ambition and the depth of Germany's industrial crisis. When American engineers first examined that Tiger II in September 1944, they expected to find a formidable weapon. They found instead a machine that revealed more about the state of German industry than any intelligence report could convey. The armor was thick but brittle. The gun was powerful, but the platform that carried it could barely function. The engineering was sophisticated, but the manufacturing was failing. Every component told the same story. Germany could still design excellent weapons, but it could no longer build them to the standards its designers intended. That discovery, documented in technical reports and field assessments, changed how Allied commanders understood the German military threat in the final months of the war. The Wehrmacht remained dangerous, capable of fierce resistance and local counterattacks, but its equipment was failing. Its industrial base was collapsing. Its ability to sustain operations was diminishing with each passing week. The Tiger II's transmission, grinding to failure after minimal operation, became a metaphor for Germany's entire military situation in late 1944. Impressive appearance, sophisticated in design, fundamentally unsustainable in practice. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.